Hey everyone, welcome to the next session. And this is all going to be only about ICMP. And when we say ICMP, most people generally think that it's all about doing a ping request and ping response, but it doesn't stop there. So the whole purpose of ICMP as a protocol was to have it as a error notification mechanism. So when I say error notification, so let's say so you're trying to reach from host A to host B over a WAN link maybe, and there is some link in the path that has a lower MTU. I'm just giving an example. So, and let's say, for example, the packet that we are trying to transmit from host A to host B has a DF bit set. Probably we might have a different video regarding the IP header. So DF bit, when there is a DF bit set, that means no device in the path can fragment that packet. So now what happens is, like, let's say a host A is connected to router 1 and it's connected to router 2 and then host B, and the MTU of host A to router 1 is 1500, and similarly the MTU of host B to router 2 is also 1500, but the MTU between the two routers is only 1000 bytes. So in this case, what happens is the device, the router 1, let's say the PC1 is sending a packet with the size of 1300 and with a DF bit set, which means no device in the path can fragment this packet. Now, when it reaches the router 1, it cannot break the packet into two so that it can send the packet out, because as you know, the MTU between router 1 and router 2 is 1000 only, and the packet size here is 1300. So since it cannot fragment the packet, it has to notify the sender, hey, there is something wrong here and I cannot fragment the packet and your packet size is too big. So that will be an error, ICMP error notification sent by the router 1 all the way to the host 1 saying that um, unable to fragment the packet or the packet size is too big kind of message. So this is one example of how ICMP can be used as an error notification mechanism. But in this video, we're not going to discuss more about the other features of ICMP. We will simply discuss about the way how ICMP is used um, well, to check the network connectivity. So when I say network connectivity, it's all about, as everyone know, the ping request and ping response, right? So to start with, let's take a packet capture on our Wi-Fi interface where we usually do. So I'm starting the capture, and I already applied the display filter, sorry, the capture filter, so that I only see the ICMP packets, right? So now I have a capture filter applied for ICMP, and we already see some ICMP echo request and reply. And interestingly, there is also some destination unreachable message in my network, which is good. So now I think I have enough packets already captured. So I'm stopping the capture here. Right. So now to start with, when in Wireshark, when you capture a packet or when you analyze a packet, and let's say you're analyzing ICMP echo request and echo reply, and if you see here in the first two packets, there is an arrow mark, the forward as well as the backward. So this indicates that these two are related to each other. So this is the ICMP request, and the second packet is its corresponding ICMP echo response. So that's how the Wireshark, I mean, that's one of the helpful built-in functionality of Wireshark for us to easily go through the capture to see, okay, whether we got the response for each request. Now, how does the Wireshark knows that this second packet is indeed the response for the first packet? Because if you see, there is an echo request here as well, and echo reply here as well. So why can't the Wireshark link these two packets? Why is it linking only these two packets? And interestingly, a point to notice, this arrow mark will only appear when you click on the on any packet. Like, let's, if I click on this packet, okay, if you see here, there are two echo requests and two echo. Okay, they are going for two different IP addresses. But if I click on the first packet, you can see that the response is the third packet, which is this echo reply. Like in case if they both go to the same destination, this will come as handy to clearly identify which response belongs to which request. Now, the interesting thing to note in ICMP is, let's take a look at the ICMP echo request as an example. And we are not going to discuss about Ethernet header or ICMP header, sorry, IPv4 header here. Let's dive into the ICMP header here. Now, to start with, there is something called ICMP type. So here the type is 8. So the type 8, usually the type 8 refers to the ICMP echo request, and if it's a reply, the type will be 0. So that's how the device knows that whether, or it can be either the device or even the Wireshark when it um, conceals the packet, right? So whether it's an ICMP echo request or reply, like whatever you see here in the info field, like it clearly says for us it's an echo ping request and ping reply. But how does it say it? It's all based on this field. Now, one more interesting point to note here is, so whatever you see in the Wireshark inside this parenthesis, they are Wireshark intercepted. Like they are not in the packet. Again, so if I highlight this type 0, and if you see in the third section, what is highlighted, it's only 0, 0. There's nothing mentioning that it's echo request or echo reply or whatever it is. It only says it's 0, 0, and Wireshark knows that if the type, and Wireshark also knows that the first field in the ICMP header is always the ICMP type, and if it's 0, that means it's an echo request. Sorry, echo reply. I'm sorry about that. So now moving forward, so let's say, so let's ignore all these things, and if you go back to, if you go all the way down to the identifier and sequence number, so these are the fields that are used by the operating system to distinguish ICMP, which reply belongs to which request. So let's say, for example, I have two terminals open, and I'm trying to ping the same destination, like let's say ping 4.2.2.2. So if you see here, I have two terminals, and I'm going to ping my default gateway from from the same terminal. So ping 192.168.1.1, and I'll do the same thing here as well, 192.168.1.1. So no response. Is it correct? Okay, sorry, it's supposed to be 0.1. So my default gateway is not 1.1, it's 0.1. So let's change it to 0.1. Okay, there's a response. Now, the question here is, so I have two terminals, and you can see here the sequence number is 0, 1, 2, 3, 4, and here also the sequence number is 0, 1, 2, 3, 4. But how does the Wireshark knows that this response comes with the, okay, one more point to note here. So when we send an echo request, we'll be sending with all these fields like identifier and sequence number and some random data. And when the device responds to this ICMP echo request, it is expected to send back a reply with exactly the same information, starting from the identifier, sequence number, as well as data. So that's how the receiving device or the ICMP request initiating device knows that the response it received is indeed belong to the request that we sent, right? So okay, so as an example, this echo request belongs to this echo reply. So if you see the data field, these two are exactly same. Okay, so now, so what is this identifier? And you also see like BELE and BELE. So let's quickly go over them. So identifier and sequence number are two different ways of differentiating each response from one another. So, I mean, it's all used by the operating system. So in my case, since I have two terminals open, and okay, I did not start the capture. Let me start the capture. Oops. I will do it later. Sorry. Okay, so I have started the capture here. So I'm going to, okay, there's a ping going on here, going on there. Let's stop the capture now. Okay, so, and one more thing I wanted to notify or I wanted to inform here is, okay, let's say I want to, you see here this every column in the Wireshark, and what if you want to add something new or if you want to delete something from here. So now for this purpose, I don't really want the identification, so I can remove the identification. I can remove this, I can remove almost everything else. So I'm going to add this identifier as a column, so apply as column. You can see now it's in the column, and I'm also going to add the sequence number, apply as column, right? So now, so what happens is any echo request going from this one, the first terminal window will always contain the same identifier. So if you see the identifier 6381, so I can also filter the packets with this identifier. I can apply a display filter with the identifier. So I have to just right click here, apply as filter, selected. So you can see all the packets only matching this identifier. And if you see the sequence number for every ping request, the sequence number keeps on incrementing. Okay, I don't want this identifier now, I'll remove it. So that's how the Wireshark or even the receiving device knows that this response, even though the sequence number is exactly same, like 38 here, but this response belong to the ping request sent by the terminal 1, and this response belong to the ping request sent by the terminal 2. Now, one thing to note here is, so what is this BE and LE? So if I click on this BE, and you can see in the third section, the raw data, we see it's highlighting 1A and AF. Let's click on this one. And oh, it's highlighting the same data in the raw data field. So why do we have two different fields, BE and LE? They're exactly the same thing in terms of when the data which we transfer on the wire, but it's just the reverse of each other. Like if you see the the identifier here is 1AAF, and here in this case it will be AF. The last two will be in the first, and that is the little Indian is what they call it as. It's called as, and the first two will be at the last. So it will be 1AAF, that becomes AF1A. And the same thing applies to the sequence number. That's mainly because some operating systems uses the BE format and some operating system uses the LE format, but it's kind of irrelevant for us while we are going to the packet capture. We have to just focus on either BE or LE, and that's pretty much all it is. Now, so what I mentioned about BE and LE is like for the, I mean, it's all depends on the operating system. So operating system may assign a different identifier for each application. Like in this case, the application is a terminal, and I also have a ping application, as you see here, the ping status application. So this is also doing the same ping. And if I change the IP address to be 192.168.0.1, that will be a different application initiating the ping request and expecting a ping response. So there can be a different identifier assigned for this application. Okay, all right. So that is how the Wireshark or the receiving device knows that which response belong to which request. Okay, and the data field which we talked about. So whatever the responder, the responding device responds with ICMP, whenever it responds with an ICMP echo reply, it will copy the same content that it received in the ICMP echo request and send it back to the same sender. So this will help us understand the end-to-end MTU, or what is the maximum size that can be transmitted from the host or the source all the way to the receiver. And so that, because for example, let's say you're sending 1,000 bytes packet and all you're getting back is a 20 bytes packet, and you're troubleshooting something related to the MTU on the network, and you will have no way to understand whether the end-to-end bidirectional MTU is what you expect it to be or not. So that way, the response will, if the response also contains the same size of data, that same size as well as the same data which you are transmitting, that will help you understand. Let's say, for example, you're doing a ping with the size of 1400 bytes, and if the response is also successful, provided, okay, let's say if you're doing a ping with the DF bit set, and if the response is also successful, that indicates that end-to-end bidirectional, the total size you can transmit, or the minimum size you can, the maximum size you can transmit is, okay, I'm sorry, the minimum size you can transmit is 1400 bytes. You never know what is the maximum size unless you increase the packet size from 1400 to maybe 1460 or 480 or whatever it is. So that's all about the basics of ICMP. So if you want to know the various types of ICMP, you can just Google. Let me show you. Right. So if you see here in IANA, so there are various ICMP types available, and that's what I said in the beginning. Like ICMP, it's not just used for the ping reply and ping request and response. There are so much the ICMP can do. That can help you troubleshooting what is happening on the network. And especially like when you're troubleshooting some kind of connectivity issue in the network, checking for any ICMP unreachable or ICMP TTL exceeded kind of messages can help to understand what is exactly happening on the network. So maybe the next video or in the upcoming videos, I'll try to cover one of the video explaining all the other ICMP types that are commonly used, so that it will give some good understanding about the usage of ICMP. Thank you for now.